All right, everybody, good morning and welcome. I hope that you are starting off this week on a good note, a new month. It's been very summer-like, not February-like. I went hiking on Sunday and sweated up a storm. It was so hot out there. No shade whatsoever, but maybe it'll cool down again. We'll see. I hope that things are going well. Just a couple quick comments. First of all, there is a homework assignment due tonight. It's a pretty chill assignment, but I will be around. So if you have some questions on it, you can ask me. I'm also going to try to save a little time today to take some questions that might get thrown up on that side board before we get out of here. So that's the first thing. The second thing is there is going to be another assignment at the end of the week that you need to turn in. And that one is based on what we're going to cover today. I'll take some questions on that assignment on Thursday. That, of course, is assuming that you tried to start that assignment by Thursday. The assignment you're doing for today is really pretty chill. The one for Friday is quite the opposite in the sense that it's fairly tedious. As you'll see what I'm going to explain today, it's kind of a tedious process that we're going to learn. So you won't want to do Friday's homework when you're really tired or when you're not focused or when you're distracted by a lot of things. So just plan that into your schedule a little bit. It's an important assignment for sure because it involves skills that we're going to be using for the entire rest of the semester. So I definitely want you to try to pick a good time to take that on. That's really all we have on the immediate horizon is just those couple of homework assignments for you. Does anybody have any questions so far about any of that? Raphael?
The PDF is it in the files?
Yes, this I'll talk about this in a minute. This is a document that is in the special handouts folder in Canvas, so you have access to it. Actually, what it is this PDF, and maybe I should put my camera on it. This PDF is the notes that go along with that 7-minute video. I know I made you guys take the notes. That's because I've learned that students learn it better when they write it down for themselves. So you all took notes on that 7-minute video about basic matrices, I think at the end of last week. But just in case you want a really polished version of those notes, I did write it up as well for myself. And I've got this document in Canvas in that same folder that's got, all the special handouts. So the one that had the different types of differential equations that we've learned, the one that has the integration table, and so on and so on. So hopefully that's clear. Well, I don't know how this is going to go today. I went swimming this morning, which I do a lot, but my ears have been plugged up all morning. I still can't hear. If you're in the back row, you might have to get my attention. Because I don't know what my things aren't draining out the way they usually do. Anyway, that's just my problem, not yours. On the board over here, I did my usual recap of what we did at the end of class last week. Let me just talk through this really quick, and then I'll tie it in with that handout also. We started talking about matrices on Thursday last week. A matrix is just an array of, say, m rows and n columns. So it's just like a block of either numbers or functions. They're just arranged into this array. And today we're going to talk a lot about matrices and what we can do with them. But there's just a lot of terminology. If the number of rows and columns matches, so if the m and the n are the same, then when you draw out your matrix, it'll look just as tall as it does wide. So it has kind of this square shape to it. So it's kind of a square shape. So we call it a square matrix. And in this case, there's a lot of other definitions that go along with having a square matrix. And some of them are on the handout, and I'll get to that in a second. I also want to remind you about this concept of transpose. On Thursday last week, we were talking about the different operations on matrices. And one of them that you can do anytime is you can swap the rows with the columns. So what that would do is change your matrix to being n by M in that case. So the number of rows and the number of columns would just get swapped, and the positions of the M and the N would, of course, also get swapped in that case. So you can always do this for any matrix. You can take a transpose of that matrix. This door got locked again. Thanks. You just open that for me. Thanks. So now, if you transpose a matrix, it's probably not going to be the same as the original matrix. If you swap the rows and the columns, there's no reason to think that they would be the same. And in fact, if the M and the N are not the same, then these two matrices, A and A transpose, they won't even be the same size in that case, right? So the only way that A and A transpose could be related to each other at all is for a square matrix. And I talk about that here. For a square matrix, it is possible that when you transpose that matrix, so guys, if you have an N by N, if you have an N by N matrix and you switch the rows and columns, the matrix will still be N by N. And it might just have all of the entries unchanged, right? And in this handout here, I call this a symmetric matrix. So a symmetric matrix is one where the A transpose is equal to A itself. These are very important matrices in linear algebra. And I gave an example on this handout you can see here. Like if you take this matrix A, B, C, B, D, E, and C, E, F, and if you switch the rows and the columns, nothing changes, right? See, the first row is A, B, C. The first column is A, B, C. If you swap them, nothing changes, right? Same thing with the second row and the second column. Same thing with the third row and the third column. So that's a symmetric matrix. Aij is equal to Aji. Very, very important that we can recognize that. Also, we have the concept of a skew symmetric matrix. This is very similar, but this time when I swap the rows and columns, it should be equal to the negative of the matrix that we started with. So you kind of pick up a minus sign everywhere. So just take a look at this example with me. If I have the first row being 0, 1, and A, and I transpose this matrix, then the 0, sorry, I said 0, 1, and A, I meant 0, A, and B. If I transpose 0, A, and B, it becomes into the first column as 0, A, and B, which is the negative of what you see there right now. So there's a minus sign that gets picked up in the case of swapping rows and columns of a skew symmetric matrix. Notationally, it's just saying here, guys, Aij is the negative of Aji. The subscripts, right, they identify rows and columns for us. By the way, if you wanted to look at, say, A11, A11 would have to be equal to negative of A11. If I just put the J and the I value both equal to 1, A11 has to equal negative of A11. Well, that means A11 better be 0. The only number that I know that is its own negative is 0 itself, right? So A11 is 0. Same thing with A22. A22 is equal to negative A22. So the A22 value must be 0. Okay, so it's real easy to see that. For a skew symmetric matrix, you have to have these zeros kind of going down from the top left corner to the bottom right corner. This is something called the main diagonal of the matrix, right? If I go from the top left to the bottom right, it's the main diagonal. You don't talk about a main diagonal unless it's a square matrix, okay? So any other size, you wouldn't really make any definition of a main diagonal. So all of the diagonal values are 0, and all of the other values are just negatives of one another across that. I like to actually, almost in my mind, I draw a line down this diagonal for myself, and I just imagine what happens as I reflect across that line, right? That's kind of the point. Yeah, go ahead.
Maybe you mentioned it earlier, but again, could you explain the representation for the IJ? Like, what do they mean?
Yeah, so Aij is just the entry in row I, and and column J. So it's a particular slot in this big matrix. Yeah,
Okay.
exactly. So that's symmetric and skew symmetric matrices. By the way, as a note, let's do our first little practice exercise, see if everybody's awake this morning. What would be the conclusion if I had a matrix that was both symmetric and skew symmetric at the same time? If A, which is n by n, is both symmetric and skew symmetric, then anybody want to take a guess what that would tell me about the matrix? Yes. It would have to be all zeros. Take a look, guys. If A transpose is equal to A, but is also equal to negative A, well, then A has to equal negative A, right? So then since A transpose equals A and A transpose equals negative A, we have that A and negative A are the same thing. The only thing I know of in the whole mathematical world that is the same as its negative is 0. So that A is equal to 0. Now, when I say 0 here, I don't mean the number 0. As you know, this is going to be representing a matrix. And in this case, it's an n by n matrix. So I'm going to denote that as 0 sub n. This actually comes up a little bit later on the sheet here. If we go down to item 6 on this handout, again, this is the same notes that you guys already took on the video over the weekend. But a 0 matrix is just a matrix filled in completely with zeros. Yeah. So if a matrix was both symmetric and skew symmetric, it would have to be just the 0 matrix itself. Couldn't be anything else. All right. I also talked in this handout, and I talked in that video that you watched about upper and lower triangular matrices. Okay, so just to remind you here, upper triangular matrices, I've got examples to show you as well. Upper triangular matrices have to have zeros below the main diagonal, right? Which is to the southwest corner of the matrix. Zeros all below the diagonal. The numbers that are on and above the main diagonal could be anything in theory, including possibly additional zeros, right? So you could have some of these other letters also being 0, but what's required is that the numbers below the main diagonal have to be 0. That's an upper triangular matrix. Kind of looks like a triangle, doesn't it? The values that are filling in the upper right corner of the matrix kind of are shaped out as a triangle. And lower triangular matrices are just the opposite of that. A lower triangular matrix is just a matrix where there's zeros above that main diagonal, right? And then putting the two concepts together, we get a really important idea, which is the idea of a diagonal matrix. This is just a matrix that's both upper and lower triangular, meaning that there are zeros above the main diagonal and everywhere below the main diagonal. So when you look at the form of a diagonal matrix, there's a lot of zeros in that matrix. The only places where you might have some different values are directly on that main diagonal. Right. So that's a matrix that's both upper and lower triangular. By the way, this only makes sense for a square matrix. So I don't talk about non-square matrices being triangular or diagonal or anything like that. Yeah. So with that in mind, I think I'm going to stop for just a second and do one of your homework problems for you. It's number 32 from section 2.1, which somebody put on the board over here, and this is as good a time as any to do it. So let's just see how we could explain number 32. We could kind of use it as a little practice problem, and we can just work it together to make sure we understand it. What it says here is show that if A, which is n by n, so we have a square matrix here. if we have an n by n symmetric, if A is symmetric and upper triangular, then A is diagonal. A is a diagonal matrix. If we have a matrix that's both symmetric and upper triangular at the same time, then it has to be a diagonal matrix. So this is a sort of a proof, actually. They're asking us to show this. So if I'm proving something like this, then I'm going to need to give kind of like a general verification of this fact. It would not be good enough for me to just write down an example of a matrix right now. If I just write down one example of a matrix, that doesn't show the general nature of this statement. This is supposed to be always the case for any matrix. If it's symmetric and upper triangular, then it's going to be diagonal, right? That's what we're really claiming here. That's what we're really saying. So, guys, if a statement was false, if it was not true, and you wanted to convince me that something was not true, then sure, you could write down one example of something that shows that it was. If I made the statement that all Saturdays are sunny, right? And you wanted to show that that was a false statement, all you would have to do is wait until finally there was one Saturday that was not sunny, and that would convince me, right? So one counterexample is always good enough for a false statement. But when something is true, like this one, this is true, we have to give a generic justification. Okay? So let's see if we can do that. It's not very long, but it does involve writing a couple of sentences, I think. So the point is that since A is upper triangular, all entries below the main diagonal are 0. Okay, and that's what this sort of example here shows. Again, I'm not doing an example to do my solution, but you can see it in the example here. All of the entries that are below the main diagonal are 0. However, because A is symmetric, which is the other part of it, because A is symmetric, whatever's going on below the main diagonal has to mirror or be the same as what's going on above the main diagonal, right? Because that's how symmetric matrices work. So I'll add that here. Since A is symmetric, add this part as well. So since A is symmetric, this implies that all entries above the main diagonal are also 0. Okay, so we're sort of told that all of the entries below the main diagonal are 0, and because it's symmetric, that implies that all of the entries above the main diagonal are also 0. Well, in other words, A is also lower triangular. If all of the entries above the main diagonal are 0, then that matrix is actually lower triangular as well. So A is lower triangular. By the way, this is just one way to write it. You're welcome to copy my notes exactly and turn it in. Hopefully my grader doesn't take off points. Otherwise, I might have to get into a little bit of a fight with them about it, but hopefully this will all be good. Well, look at this, guys. A is upper triangular to begin with, and now we've figured out that it's also lower triangular. Well, look at what this says here, guys. A matrix that is both upper and lower triangular, that's a diagonal matrix. So we get our conclusion. So thus, A is a diagonal matrix. Awesome, awesome, awesome. Okay, so that is a quick little paragraph to explain number 32 from that first section on. Oh my God. I probably just broke this thing.
That's solid.
What's that?
Still good.
Yeah, maybe. We'll worry about it later. You guys didn't see that.
The camera's just here.
Yeah, exactly. I might have to destroy the evidence. Okay, anyhow. No, it's all good. Does this make sense? Everybody good with that? I dropped that thing on my toe. Ouch. Okay. Yeah, so anyway, this is a nice handout. Somebody was asking me where you can find it. I just wanted to point this out. Oops, I closed our Canvas page. If you go into Canvas, real quick, in the files section, so if I hover over the files section here, I've pointed this out to you guys before. There's a special handouts folder. And if you open that up, you'll see down near the bottom, there is a special matrices handout. So that's the one that I was just pulling up right now. And you can find that anytime you like, but probably you already have your notes on it because you took notes on that video over the week or over last Friday on the homework that you returned in. So I think without further ado, I'll go ahead and take that screen down. Are there any questions so far? So far, so good. Okay, so we talked about transposing a matrix. On Thursday last week, we also talked about doing calculus. So we can take derivatives, we can take integrals. We can also do algebra. So there was a addition, subtraction, there was multiplication, and there was scalar multiplication. Is everybody feeling okay about most of those operations? We know how to do the matrix multiplication. Does anybody need another example of that? It's where you do the dot product. You take the rows of the first matrix and you dot them with the columns of the second matrix.
You do it.
Want to see one real quick?
Yeah.
Let's just practice one more example of matrix multiplication, and then we're going to forevermore move on. But it has been 5 days, and this is absolutely critical. So if I had a matrix A, which was, let's just make this one 3 by 2. Let's suppose it has a 3 and a 1, a 0 and a 4, and a -1 and a 2. Okay, and then if I take another matrix B, this matrix, I'll just make up something here. Maybe it's 9, 8, 7, 6. And just as an example, then let's try to compute A times B. Let's try to compute A times B. Well, first of all, we should ask ourselves, can we compute A times B? Let's check it out. What's the size of matrix A? 3 rows by 2 columns, right? And what's the size of the matrix B?
2 by 2.
2 by 2. So am I able to calculate that?
Yes.
I can, right? As long as, remember, this number here and this number here, they have to match. They have to match. So 2 and 2, they do match. The resulting matrix will have what size? 3 by 2, exactly. It'll be 3 by 2, so it's going to have 3 rows and 2 columns. And to figure out the entries, I just take dot products of the rows of the first matrix with the columns of the second matrix. So let's do the 1, 1 entry. It'd be 3 and 1 dotted with 9 and 7. That's 27 plus 7, 34, right? 34 for that value. And then the 1, 2 entry requires me to take the dot product of 3, 1 with 8 and 6. And that's going to be 24 plus 6, which is 30. Okay? On the second row, I'm going to dot the 0 and 4 with both of these two columns. And so I'll have 0 plus 28, which is 28, and then I'll have 0 plus 24, which is 24. It's going to look like that. And finally, on the bottom row, I have to take -1 and 2 and dot that with each of these columns. So the first one would be -9 plus 14, which is 5. And the second one would be -8 plus 2 times 6, which is 12, -8 plus 12, which is 4. And so we get that for the answer. Okay, you don't really have to show your work here. You're just writing down the values as you go. So that's the good news about it. I will note here, I mentioned this on Thursday, that if we had tried to multiply B times A, we would then be putting the 2 by 2 matrix on the left and then the 3 by 2 matrix on the right of that, and that would not be compatible. That would not actually work. So this one doesn't exist. Okay, and in general, guys, A times B is not usually equal to B times A, right? It's not usually going to work that way. So have to be a little bit careful not to switch the order of any matrix that you ever see. Even if both of these exist, they're probably not going to be equal to each other. They're probably not, right? So as a quick example, I believe this one might be on the homework that you're working on this week. If I wanted to say cube the matrix A plus B, you know, this is A plus B times A plus B times A plus B. So we still use powers with matrices the same way we do for numbers, which is that we just multiply the expression by itself again and again and again. And I can start foiling this out. Maybe I'll FOIL out just this first part to begin with. But I can't simplify it really as I go along. So I have A times A, which is A squared here, and then plus AB, and then plus BA, and then plus B squared. And you cannot simplify that. You cannot write that as 2AB because AB and BA are two different animals. They're not the same thing. And then I can go a step further and like FOIL it all the way out. These 4 terms multiplied by these 2 terms, I can do it distributing it, but I can't switch the order of anything. So I can take A squared times A, which is A cubed, and then I can take A squared times B, which is A squared times B, and then I can take AB times A, and I have to just leave it as ABA. I can't simplify that. And then I have AB times B. Well, I can write that as AB squared. And then the next one is BA times A. Well, that's BA squared. And then I have BA times B, which is BAB. Okay. And then finally, the B squared gets multiplied by A. And the B squared gets multiplied by B. And that's the expression that we end up with. 8 terms, none of which are combinable. None of which can be grouped together because I'm not allowed to switch the order of anything that I see there. So if you were doing this in high school with regular variables, you would totally clean that up into, I think, only 4 terms instead of 8. So when you're working with matrices, you've got to be really careful about this. The order of the matrices cannot be switched as much as it's our natural inclination to do that. That look okay? I probably should write down some properties that do work. I've talked about what doesn't work. We can't switch the order of any of these matrices, but there are some things that do work, and I want to give you an idea of some of these. So let's come back over here. We'll make a little list of some properties of matrix algebra. Okay, so some properties, I'll make it as a list here, guys. Properties of matrix algebra. Some properties of matrix algebra here. So let me just start off by saying we're going to take matrices that I'll call A, B, and C. So I'm going to say let A, B, and C be matrices of appropriate sizes. Okay, so these properties won't make any sense if things aren't appropriate sizes. So I'll explain what I mean here in just a second. But I've got 10 of them here. This is going to be 10 things I'm going to write down in this list. So the first one is, and these are really easy, guys. This is not rocket science. If I take a matrix and I add the zero matrix to it, so this would be the matrix of all zeros. What do you suppose you're going to get when you add the matrix of all zeros to something? Back to A again, right? You just get back whatever you started with. So the zero matrix really does act like zero. Nothing too interesting about that. Also, as a second property, if we take the number 0 and multiply it by A, we actually end up getting the zero matrix. So if you remember scalar multiplication, that's what I'm doing here. I'm simply taking everything in A and I'm scaling it through by 0, which just means I'm going to zero out every single entry of the matrix. Yeah, so that's, of course, very that's very expected. The third one is that although you cannot switch the order of anything with matrix multiplication, you can drop your parentheses. So this one just says if you take A times B and then multiply by C, you'll get the same result as if you start with A and multiply it by the combined product of B and C. Notice I did not switch the order of anything. A is first, B is second, and C is third on both sides. What this really says is that parentheses don't matter. You don't have to use parentheses. So if you wrote down ABC on your paper somewhere, nobody could give you a hard time about that. Because if you write ABC, maybe you're thinking about it this way, and I'm thinking about it this way. It doesn't actually matter because we're both going to agree on what it's equal to. Okay, so this just says that parentheses don't matter. This is called the associative property. Parentheses don't matter. It's actually a royal pain to prove that one. It's not very interesting, so I'm not going to do it because it's not very enlightening. You don't really learn a lot by doing the proof. It's just you get tired with all the subscripting that goes on with doing matrix multiplication. So we'll just leave it at that. Number 4, this is the one that combines multiplication with addition. So if I want to take A and multiply it by the quantity of B plus C, that is exactly what you hope it would be. It's just AB plus AC. Totally okay with that. And number 5 says you can do the same thing with the addition on the left side. Again, I'm being careful about left versus right. So if I had A plus B on the left and then multiply that by C, well, that just becomes A times C plus B times C. Okay, so nothing surprising going on there at all. Number 6 is a very easy one. If I take an M by N matrix A and I multiply it by, okay, so here I didn't remind you about this one from the video, the identity matrix. This is I sub N. Let's do it right down here. I'll just remind you, the identity matrix is the one that has zeros going down the main diagonal of it. And zeros going down all of the entries except the ones going down the main diagonal of it. Okay, so you have ones on the main diagonal like that. What's special about this is that when you multiply this matrix by anything, which is what I'm going to do right here, it leaves the matrix alone. it just leaves it exactly the same. Okay, if you want it, you could test that out. Just put some random matrix here and then just do that dot product process that we just practiced a moment ago. Just do it. So if you take, each row here and dot it with each column here, you will literally just reproduce the matrix on the right again. And I've actually cheated here. I put the identity matrix on the left side. That's actually another property. So if I have an M by M identity matrix multiplied by A, again, I'll just get A back again. Doesn't really matter whether it's on the left or on the right. Okay, so that's your good old identity matrix for you. Okay, so far so good. Any questions? I've got 3 more. I said there's 10 of these. The last 3 properties I want to write down have to do with the transpose. So number 8, maybe you guys can tell me, if I took a matrix A and I transposed it, and then I transposed it again, what do you think I'd end up with? The original matrix A, exactly. So if you swap the rows and columns, and then you swap them back again, right, which is what that's doing, you get back to where you started. You get back to the original matrix A. So a double transpose just sends you back to where you were before. No surprise there. Okay, number 9. If I have A plus B and I transposed that. So this is where you're first adding 2 matrices together, and then after that you swap the rows with the columns. Does anybody think that they know what I might want to put on the right-hand side of the equal sign that would be the same thing as doing that? Here? Yeah, exactly. It's just A transpose plus B transpose. It makes common sense that you could swap the rows and columns first separately and then add the matrices together. You'll end up at the same place as you would have otherwise. Yeah. And one more. What do you think would happen if we took the transpose of A times B?
Would it just give you BA?
Close. Quite. Do you have a guess? This is a tricky one. This is a little bit of a tricky one. Let me come back to this example we warmed up with over here for a second. Because we've already kind of done some work on this example. I wonder what would happen if we wanted to. So obviously, if this is what A times B is, then in the example above, it's right here, then A, B quantity transpose, that's just the transpose of this matrix. So the first row would become the first column, right? The second row becomes the second column, and the third row would become the third column. Yeah. What a lot of people think is that this would just be A transpose times B transpose. But if you look at what A transpose is, A transpose, just the original A, if I transpose it, I get 3 and 1 as the first column, 0 and 4 is the second column, and -1, 2 is the third column. Whereas B transpose just becomes, let's see, 9 and 8 on the first column, 7, 6 on the second column. And can I even calculate A transpose times B transpose? No. You can't even do it. This is 2 by 3, and this is 2 by 2. These numbers do not match. Yep. So I cannot calculate A transpose, B transpose. So the most popular answer that people try to give me here is that it should be A transpose times B transpose. But we now see that that actually would not work. Because we can't even calculate A transpose times B transpose, let alone end up with this matrix as the answer. So is there a tweak to that might actually work, Aaron?
Square matrices are the same.
If they were both square matrices, we wouldn't run into this problem right away. But I want a formula that's gonna work whether the matrices are square or not. Channel?
So would you do B transpose times A?
Yeah, that's it, guys. That turns out to be correct. B transpose times A transpose. If you come over here and you put this matrix on the left and this one on the right, and you do the calculation, I promise you, you'll get exactly this matrix. I'll let you check that. But that is right. So here again, we see that the order that the matrices are written in is critical. It makes a difference, and we can't be random about it. We have to make sure that things are written down in the correct order.
You'd have to take the transpose first, right? Before multiplying them?
Yeah, these both have to be transposed individually on the right-hand side first, and then we can multiply them together. So far, so good? One more comment here, and then I think I'll be ready to move on to the next sort of general topic. But I want to tie this back in. That's it for my list of properties, by the way. I want to tie this back into the linear systems of equations. So we haven't been talking about that today. So far today, we've been just talking about matrices for their own sake. But I want to try to make a little connection for you here. Let's just recall that a linear system would look like the following form. Okay, now I'm going to write it down in generic variables right now. So the first equation in my system might be a11 x1 plus a12 x2 and dot 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 up to a1n xn equals b1. And then my second equation would be maybe a21 x1, a22 x2, and dot 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 up to a2n xn equals b2. This is just another equation in my system. And we might have a lot of equations. I'll just put dot 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 here to show that we could go down the board for a while. But we finally get to the last one, which might be a m1 x1 plus a m2 x2 and dot 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 plus a mn xn equals bm. So this is my linear system. And remember that the xi's, those are the unknowns of my system. And the goal, squeeze this right here if I can. The goal is to solve for the unknowns. And I'm going to add, if possible. If possible, the goal is to solve for those unknowns. This is to solve for those x's. Now, last week, when I talked about linear systems, I explained that you can just literally take the data from this system and put it into what was called the augmented matrix for that system. So I'm just going to recall that we had this thing called A sharp. There's at least one homework problem for tonight where you're being asked to like write down the A sharp matrix and put that information down. The A sharp, guys, is literally, you don't really have to think too hard. You just have to copy the numbers from your original system into this matrix. And remember, we put a little bar over here to separate the right-hand side values. And it just goes down all the way to the mth row, which just gets filled out like so. So I just grab all of those A's and all of those B's and throw them into A sharp. The unknowns don't actually appear physically in this augmented matrix. Remember that the unknowns are sort of attached to these columns somehow, say x1 through xn. The unknowns are there, but they don't appear in the matrix. They're kind of behind the scenes when we put down this augmented matrix. Okay? But there is another way, besides just doing A sharp, there is another way that we could represent our linear system using matrices. So another approach or another way to show the linear system. I'm going to give you another way. This one I have not talked about before. So this one I have not talked about before. Let me move this over a little closer. There's another way to represent this, and that is, do you notice on the left side, A11 x1 plus A12 x2 plus A13 x3? That almost sounds like I'm doing a dot product of some A's with some X's. It's like a dot product. And in fact, I can do that. I can just take A11, A12, dot, 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 up to A1n, and I can imagine dotting it. Remember, dot products are associated with matrix multiplication. I can imagine dotting it with this column of X's here. If I was multiplying these matrices together, guys, I would do A11 times x1 plus A12 times x2 plus dot, dot, dot. And of course, this would be equal to whatever it's equal to on the right side, which would be B1. That would equal on the right-hand side to B1. And those same X's get dotted with a different collection of these A scalars on the second equation. So that's just A21, A22, all the way up to A2n, also being dotted with the same unknowns to give me B2. And we can go all the way down, just like before, and write it all the way to the last equation, which is AM1 dotted with x1, AM2 dotted with x2, and so on. And this is going to equal BM. So as an alternative approach, and I'm going to need just a little more room. I think I'll just do it right here so I don't have to move too far away. But what this is, guys, if I can just give it to you in a nutshell, what this is it's just the matrix A times this. Technically, X is a matrix as well, but it only has one column. So it's A times X equals B. So it can be just compressed into this simple notation. Check it out, guys. A is M by N. X is N by 1. And my B vector is M by 1. And the sizes are exactly compatible with how matrix multiplication is supposed to work. So this is another way of writing your linear system. I've given you two options now. Two options. One is to just write down the augmented matrix. We did that last week before we even knew how to multiply matrices together. And now that we do know how to multiply matrices together, we actually can represent our linear system in this alternative way. And in compressed form, it would read like this. The goal, somewhere I wrote it on the board already. Here it is. Goal, solve for the unknowns. Well, that translates into solve for X. That translates into solve for this X vector, right? This X vector has all of these X's in it. Well, that's fine and dandy. If I had this equation and I wanted to solve it for X, question is, what would we do? If you had a 10-year-old brother or sister at home and you had an equation and you wanted to solve it for X, what would you tell them to do?
But
Divide by 10, right? Right here. So right here, you're like, oh, I want to solve for x. Let's divide by a.
You say you can, huh?
Except, do you remember this from last week? I wrote down all the operations on matrices. We can do transposes. We can take derivatives. We can do integrals. We can add. We can subtract. We can multiply. We can scalar multiply. The one thing that I did not tell you that we could do is the one thing I wish we could do right now. I wish I could divide by a to isolate that x all by itself. Dang it, we can't do that. So we are in a pickle in what, well, we have two solutions. One is we can somehow figure out how to solve our system from the augmented matrix instead. Go back to that. The other option is to figure out some way to sort of do some kind of a pseudo division of matrices. And I'm going to talk about that on Thursday. For today, I'm going to focus on the augmented matrix way of proceeding. Okay, so there's a couple of different options here. The way that we're going to do today, the way I'm going to talk about right now, is a way that will always work for every scenario. If I give you a linear system and you want to solve for the unknowns, put it into that augmented matrix and we will always have a procedure that we can use to solve it. And I'm going to start explaining that procedure now. This is what you waited all weekend for. I got you to come back today just to hear this little explanation about how to do this. So let me make a couple of remarks and then we'll explain exactly how this procedure works, but it always works. It doesn't mean the system always has a solution, right? We said that sometimes systems might be inconsistent. It won't always have a solution, but we have a procedure that will always get to the root of the issue of our linear system. So this is really sort of covered in this next section. 2.4 is kind of where we're at, about halfway through chapter 2 right now. This is called EROs and REFs. That's kind of the title that I'm going to give to this section. And of course, I have to explain what EROs are and what REFs are. But that'll come along as we're talking through this. I'd like to sort of start this section with 3 remarks. I'm going to make 3 comments here, guys, about linear systems that I hope will all seem pretty natural. So the first remark, there's three things I'd like you guys to all understand. The first one is that a linear system is easy to solve. It's easy to solve some kinds of linear systems. It is easy to solve by something called back substitution. So I'm going to use that word here, back substitution. A linear system is easy to solve by back substitution if it is in a triangular form. I need to explain what I mean by a triangular form. Let me do an example to kind of illustrate it. What's an example of a triangular form? What if I had 2x minus 3y plus c is equal to 6? And then I have maybe another equation which might be 4y minus c is equal to 8. And then I have one more equation which might just be z is equal to 4. If this was my system. So my unknowns here are x, y, and z. My goal is to solve for those unknowns. If I handed you this problem and asked you to solve for x, y, and z, do you think you could do it pretty easily?
Yeah.
I think so. What would you do?
Plug in a 4 for z in the second one.
Start at the bottom, right? Z is equal to 4. You can take that value, plug it into the previous equation, which then allows you to solve for y. And once you know what y is, then you can plug both y and z back into the first equation and solve it for x. That's what back substitution is. Okay, so in this case, we would get, we find that z is equal to 4, obviously, and then by plugging that into the previous equation, y is equal to 3, and then plugging both y and z into the top equation, we can solve for x, and I'll save you the mental math. It's too early in the morning probably still, so I'll just do it for you. It's 11/2, okay? Now, this is not a good habit to get into of how to write an answer. So the solution that I would want you to write down, and this is something you will be doing on Friday's homework assignment, I want you to write your solutions to your linear systems, assuming they exist. I want you to write them as sets of solutions. So I'm going to use a squiggly braces, and then I'm just going to list in an ordered triple the values of x, y, and z. So the x should come first because it's the first unknown. It's 11/2. And then y is 3, and then z is 4. So this would be the solution. And I just want to get into a good habit of how to write the solution to our linear system in a nice notation. So we can just put it into a set looking just like that. Okay, so is everybody on board with this first remark? If I can just sort of back substitute in a, see, it's kind of a triangular shape here. So if I have a triangular system like this, I can just solve it by kind of a back substitution. Okay, the second remark is, this one takes a little bit more to talk about it, but we can do this here. No solutions to the system. So item number 2 here, guys. No solutions to the system are gained or lost. No solutions are gained or lost if we perform these operations. Okay, I'll put another colon here, and I'm going to make a list of some things that we can do. All right. No solutions are gained or lost if we perform these operations. I'll call these maybe A, B, and C here. So the first one, I'll call it A. This is where we permute two equations. And I'm going to, by the way, we're going to have some notations for these operations that I want you guys to sort of adopt. If I write Pij somewhere in the work that I'm doing, it means I'm going to permute, or just switch, in other words, switch the I and j equation, right? Just permuting the two equations. I'm pretty sure you guys would all agree with this. If my system of equations had been written like this, you don't need to write this down, but this is the system. If I compare this system of equations with this one, what you notice is that all that happened was the second and third equations got permuted, so that the z equals 4 equation is second, and then the 4y minus z equals 8 is third. So you can see that this one is not really triangular. But if I permute rows 2 and 3, or equations 2 and 3, then I get it into this nice triangular form, and from there it's easy to solve it, you see. What my point is, guys, that even if the system is not triangular yet, I might be able to do some operations that will make it triangular, so that then it's easy to solve by back substitution. That's the whole idea here. Okay, so permuting two equations, I think that's a pretty safe thing to do. Another thing that is safe to do, we don't gain or lose anything, is the following one. Multiply, let's say, the ith equation. The ith equation, let's say we want to multiply that by some constant k, which is not 0. And the notation that you will want to use for this one is M sub I of K. M sub I of K. Does everybody agree that if I multiply the third equation by 10, right? If I multiply one of my equations through by a constant, have I gained or lost anything? Z is still equal to 4, y will still be equal to 3, and x will still be equal to 11 over 2. There's nothing gained or lost by doing something as simple as that. So you can multiply an equation through by a constant. Okay, and then there's one more. This one's actually the most important one, but it's also maybe the trickiest one, which is that we can add, this is the third one, guys, we can add K times the ith equation to the jth equation. We can add a multiple of one equation to another equation. So I might obviously have to identify what my I and my J are. These are two different equations in my system, and I'm going to add a multiple of one of them to the other, okay? And the notation for this is going to be A sub ij of K. So I can take K times the ith equation and add it to the jth equation. Okay. And again, that is a safe operation to do. We will not gain or lose anything in terms of solutions if we perform that. So none of these are going to harm our system at all. And these operations here, guys, they collectively go by the name elementary row operations. So these are called elementary row operations, and that's usually abbreviated EROs. So now you see part of the title of this section we're talking about right now, EROs. That's talking about elementary row operations. Okay. So far, so good. I've got two of my remarks out of the way here. This is the big one. This is the one that's the most important for us. If I hand you some random linear system, right, you might be wandering around in the wilderness trying to think, well, what EROs should I do to the system to get it into this triangular form? So that we need to practice still. Cam, did you have a question?
Yeah, so basically you can change the order as a row of the matrix, correct?
I can permute two rows of this system. I can multiply any equation by a non-zero constant, or I could add a multiple of one row to another. And in fact, I can do several of these things.
So if you do two matrices like that together,
I'm not talking about multiplying matrices yet, if that's what you're talking about. We're not multiplying matrices, we're taking a single augmented matrix A sharp. This is really what we're going to be working with. So we're not combining this with the operations on matrices from earlier. This is like a new section, new topic, new section, and don't want to get confused. Yeah. Good point. Any other questions so far, guys?
So basically, by using these, it's gonna like allow you to like solve it easier, right? Simplify it, just manipulate it, right?
The goal is going to be, for those of you who like to think ahead a little bit, the goal is going to be to take your linear system, throw it in a matrix, that's the Math 250B joke, write it as A sharp, then perform elementary row operations on A sharp to bring it into this triangular form, and from there, it should be easy to solve it by back substitution. That's the whole enchilada of how this works. Okay. But before I get ahead of myself, I have to make one more remark, and then we've got to take a 10-minute break somewhere along the line here pretty soon too. So let me make this third remark first, though, which is, and Kim was already kind of hinting at it because he was talking about doing things with the matrices. I'm talking here about the equations of my system, But those two remarks, so the 1 and 2 above apply to the rows of A sharp. So you don't have to just talk about it in the context of a bunch of equations. You can also talk about it if you've already got the matrix in your hands. You've already built this A sharp matrix and you're just ready to do EROs on the rows of that matrix. By the way, as people will sometimes ask me, am I allowed to do column operate? Can I permute two columns? Could I multiply a column through by a constant? And the answer to all of that is no, 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 no. You could not do that. If I took this system and instead of multiplying the third equation by 10, if I had decided to multiply just everything in front of the x by 10, that would change your system. It would be a completely different system. It would have different solutions. So we are only doing row operations. This is elementary row operations, not columns. Yeah. Last thing I'll say before we take a short break here, guys, is that this one worked out beautifully to turn into a triangle. You could imagine if I had, let's say, if I had only 2 equations, but they had 100 unknowns in them. So your matrix doesn't even look close to being square, right? So here's your augmented matrix. It's super wide and it's got this bar way over here. You're probably thinking, well, how is that ever going to look like a triangle? Right? It's not shaped terribly well for that. And mathematicians realized that pretty early on as well, that we can't just casually talk about triangular form here, because if the matrix gets set up in such a way that it looks really off kilter, it's really, really wide or really tall, there will be no such thing as a triangle shape to look for. So there is another sort of more fancy formal word for this. So I'll describe the process and then I'll just say what this word is. The process, I've already kind of said this out loud, but let's just write it into our notes here, guys. We're going to use EROs to convert A sharp into, so not into triangular form, that's what we would have hoped we would be saying right now, but that turns out not to be the right thing to say. We have to slightly tweak that and talk about something called row echelon form. We have to convert A sharp into row echelon form, which, by the way, abbreviates to REF, row echelon form, which is part of the title of this section right here, row echelon form. So what exactly is row echelon form? It's got to be something kind of similar to a triangular form, but a little more general. Let me write it down, and then we'll save the examples until we take a short break here. But let's just quickly write down the definition of a row echelon form. Okay, so we'll wrap up the first part of our class with just this definition here, guys. A matrix is in row echelon form if 2 things are true. There's really just 2 things that have to be true. The first one is if there are any rows of all zeros, so any all 0 rows are at the bottom. You can understand pretty quickly why I would want to put the all 0 rows at the bottom. Let me just explain to you guys that if you have a row of all zeros, you have absolutely no information of help whatsoever. If I gave you this equation, 0x plus 0y plus 0z equals, and that would be like a row of all zeros. Can you tell me anything about x, y, and z based on that? No. Because whatever values they have, they get multiplied by 0 and canceled out anyway. So these rows of all zeros are completely useless. So let's throw them to the bottom. Okay. By the way, how can I throw them to the bottom? Permute. Exactly. I can permute. If I have a row of zeros that's not on the bottom, I can permute it down to the bottom. Okay, so that's pretty easy. Okay, the second point, which is the more interesting part of it, is this is the only other point there is. There's only 2 points here. So for all other rows, the first non-zero entry. So in any other row, there will be a non-zero entry. And by the way, the first non-zero entry is usually referred to as a pivot. And while I'm at it, I'm going to show you the notation that I'm going to be using for pivots. I will be putting those non-zero entries into these little diamond shapes to really remind myself that those are pivots, because it's really important that you identify those. The first non-zero entry, first of all, it must be a 1. Well, what if it's not a 1? What if it's a 7? Reading across my row, I got 0, 0, 0, and then a 7 shows up. Can I do anything about that?
You could multiply by 1/7.
I could multiply that row by 1/7 to turn that 7 into a 1. That's exactly right. So that's a safe thing to do. So you can always arrange this to be a 1 and occurs to the right. It occurs to the right of the pivot in the row above. It occurs to the right of the pivot that is in the row just directly above. So just so we have an example of maybe a row echelon form of an A sharp here, I'll write the notation this way. Just want you to kind of see how it would be visualized here. Just going to give a rough idea. We'll do a specific example in a few minutes. So if you want to have a matrix in row echelon form, if I have any rows of all zeros, we need to permute them down to the bottom. So let's suppose we have a couple of those. Those rows of all, and there's a bar here. So if you had any all 0 rows, you throw them at the bottom. Okay. And then in all other rows, the first non-zero entry has to be a 1. So I'll circle it as a pivot, putting a 1 on it. Once I look to the right of the pivot, I actually can have any numbers whatsoever. There's no constraints on what happens to the right of that. So you could have a 1 for a pivot and then a bunch of other numbers. In the next row, the next pivot occurs to the right of the pivot in the row above it. So on the next row, you have to have a 0 here. Actually, this is going to be the key thing. You have to have zeros below any pivot. As soon as you have a pivot, everything below that pivot must be a 0. But it doesn't mean that there's a pivot immediately in the next column. You might have to go over a ways. But it's to the right of the pivot above it. And then after the pivot, you can have any numbers whatsoever. Okay, and then maybe there's one more row here. Maybe this time the pivot is in the very next column. This would be an example of a row echelon form matrix. Okay, that's kind of the shape of what it would look like. And the goal is going to be to use EROs to get your matrix into this kind of a form. Okay, making some sense? We'll need some examples, I think, to show how it works. And this is where I was talking about for the homework for Friday. You need to be like awake, not distracted, focused, because doing these EROs is kind of a tedious little bit of a chore. Let's take a 10-minute break, and then I'll come back and we'll actually do some examples of these things I've just been talking about. I've got the whole outline for you. We just need to practice it a little bit. So let's take a 10-minute break. It's right now, it's about 11:15. So take 10 minutes at 11:25 or so. We will do some examples of row echelon forms. and EROs. I'll see you then.
We have like the rows of zeros.
You could.
So it's just
Yeah.
just for conveyance or?
Just because technically the matrix should not change sizes in the middle of solving a system. So it's just out of respect for the fact that, oh, there really was 5 equations
But
here.
they're realistically.
They're realistically, you could ignore them and you would still get the right answer. So yeah, if you, actually later in the semester, I will get a little more sloppy with that too, and I'll start just crossing off rows.
Yeah.
I'll just cross this off, cross that off. But for right now, I want to try to be a little bit careful with it. Yeah, great.
Vacancies. And it's called like the first, audio entry, that was the one, we called it a leading one, so.
Yeah, it's also called a leading one.
Oh.
Yeah, it's another word, yeah.
Agree.
Yep. I too, yeah. Sure, yeah, you know, that's my office hours are for, anytime. Hey guys, I think I'm gonna go ahead and pick things back up again. It's about 11:25 or so. I also forgot to mention that today is the last day to drop a class without a W, not just my class, any class. It's also the last day to add a class. At this point, if you're not on the roster, you would need to get a permit signed by me for this class. I think I've taken care of that, but you should just double check. Remember that just having access to Canvas doesn't mean you're on my roster. So make sure you check your portal. And I think I'm just going to take attendance right now, just so I can double check one last time with my roster later today and send out any emergency emails before midnight when they really make it hard to make any more changes. So if you could just write your name down on the back of this green sheet of paper, I'll just send that around, and that would be a good way for me to just do a last confirmation about the roster, and I could check in with anybody who's gone as well. So anyhow, did anybody have any questions so far about the strategy, the big picture process, which is going to be, let me just remind you again, we're going to write down our augmented matrix. We're then going to use these three types of elementary row operations to hopefully turn it into this row echelon form so that it'll be easy to solve it from there. Okay, that's the big picture of the strategy. Caesar?
So for the pivots,
Yes.
after the first one, it can be in any order as long as it's not in that first column, which is supposed to be 0.
Right, the first column would, below this pivot would have to be all zeros.
So the other pivots can be any which way.
Well, they
as long as
still
they're zeros.
have to go down and to the right. Each pivot occurs to the right of the pivot in the row above. So, here I've gone down to the right. I skipped over a couple of columns. That's fine. Here I did not skip any columns, but it just has to be trending down and to the right. Yeah. let's practice it on an example. I'm not gonna turn this into a linear system yet. I just want to work with an actual matrix first. So I think this one will be a good starting point to practice with. So here's my matrix A. It's a 3x4 matrix. And I've filled it out there, and the question is just asking me to find the row echelon form of this matrix. So when you see a question like this, guys, one of the first things you will want to try to do is to get a pivot as far into the upper left corner as possible. Can anybody, and a pivot has to be a 1. Can anybody think of a good way to get a pivot into the upper left corner of this matrix?
Permutation.
Permuting is one way to do it. And so which 2 rows would you like me to permute, Aaron?
I guess the second and the first.
The first and second one. Okay, so guys, here's the way I want you to write this down for your homework for Friday. You're starting with the matrix A, and I'm going to use this little twiddle symbol. It's like a sideways S, a little twiddle symbol. And next to that twiddle symbol, I'm going to write down which ERO I'm going to do right now. So I'm going to permute rows 1 and 2. So let's write down what that would give us. That would move the second row to the first row and the first row to the second row. And it would not change anything in the third row. So I would get my pivot here as being a 1 in the upper left corner. That's the way it's supposed to be. Okay? So that is certainly one way to do it. Okay? Now, the pivots that are in the second or third row have to be further to the right, right? Pivots have to be to the right of the pivots above them. That means that below this 1, I have to have all zeros in order for the pivots to be over to the right further, you see? So can somebody suggest, how am I going to turn this 2 into a 0? You want to try it again?
Yeah.
Go ahead.
Subtract it.
Okay, I have 3 things: permute, multiply, and add. So when you say subtract, you really mean add, which is the right operation. Adding from which row to which row? If I want to turn this 2 into a 0.
Whichever. You could do it by the first one.
I can take rows 1. I can take row 1 and apply it to row 2 with what multiple?
2. -2.
-2. Guys, here's the Aij of k notation. That means take -2 times the first equation and add it to the second one. -2 times the first row and add it to the second one. Let's take a look at it. That actually does not change the first row at all. Even though we are using the first row to do something right now, the first row does not change. I'm going to take -2 times the first row and add it to the second row, and it will create a 0 here. Now, guys, I'm going to do all of this math just in my head, and so are you. It's going to be one of those things where you just have to stay focused on it. Okay, don't try to watch television, talk to your friend, and watch your barking dog at the same time and do this. It won't work. Okay.
You gotta be locked
So
in.
you got to really be focused in, locked in. -2 times the first row added to the second row, I'll get 0, 3, 1, and -2. So if I take -2 times the first row and I add it to the second row, these are the numbers I'll get. So for example, -2 times 3, when I add that to 4, it becomes -2. The second row is the row that actually changed. The third row also does not change at all in that process of doing it. Okay?
Oh, so those operations are only getting applied to that second row?
Only being applied to the second row. The A operation is applying a multiple of the first row only to the second row. So now we've got this guy. I still have a problem in this first column because I would need to have a 0 here as well.
She added -1.
So let's talk about it. What operation do I want to do to get this 1 to turn into a 0?
add -1 times the first equation into the third equation.
There you go. Take the -1 times the first equation and add it to the third equation. How do you figure this out? You figure it out literally by just looking at these two numbers and saying, oh, the negative of this one needs to be added to this one. So if I do that, the first row again does not change. The second row does not change. But the third row, if I take the negative of the first row and I add it to the third row, I'll get 0, -3, -1, and 2. Yeah, that's what I'll have there. Okay. Any suggestions what I might want to do from here? Let me hear from somebody different this time. Somebody different want to take a shot at it? Add the second row to the third row. So that would be A2, 3 of 1. By the way, I like that. I mean, one thing you could have said, well, you could have said, I want to multiply row 2 by 1/3 to get a 1 there. And we do need to do that, but I kind of like that you suggested that we do this one first because we don't have to do the precise order of these operations. If I add the second row to the third row, guys, it totally zeroes out the third row. It totally zeroes out the third row. And what's the one last ERO that I need to do at this point to get it into the final row echelon form?
Multiply the second equation by 1/3.
Multiply the second equation by 1/3. I love it. I love it. And so that's it. If we do that, the first row stays the same again. The second row gets multiplied by 1/3. And the third row, of course, is all zeros. And I've got my pivots circled here to show that they are in the right sort of formation according to the rules here. So this would be the answer. Actually, I should correct myself. I said this will be the answer. I think I probably should have said this will be an answer. Did everybody sign in my attendance sheet? Okay, good. I'll just make sure we got the enrollment under control. Would this be the only answer we could have come up with? I don't think so. I don't think so. Right at the very beginning, right back to the very beginning, we permuted rows 1 and 2 to get a 1 in the upper left corner. But what if instead I had said, I think I'm going to multiply the first row by 1/2? That would have put a 1 in the upper left corner too. Right? Now, if I had done that, let me just scribble over here. If I had done that, if I had multiplied the first row by 1/2, this is what the first row would have become. And presumably I never would have changed it again. So my final answer, if I had started this way, would have had that for its first row. By the way, would this have been a better way to do it? Do you think?
The thing would have been simpler.
Similar?
Yeah.
It would be similar, but
You would get the same.
you would not get the same answer.
Yeah.
But what would make this way of doing it not so good?
So now you're in it with more fractions.
Fractions. Fractions right from the very get-go would be really annoying to have to do them, especially in your head, step after step after step with fractions involved. Not really a great plan. So what we've managed to do here, guys, is we've avoided fractions all the way until the very last step. Is much less likely to make a mistake that way. If you start working on the homework for Friday and you start getting messy, awful fractions in some of your work, it probably means you want to rethink it because there might be a nicer way to actually organize and choose your EROs. Yeah, Caesar.
There's no scenario where there might just be like one options.
Well, there might be what?
Like one answer.
No, there will be lots of right answers for row echelon. We have 30 people in this room. We could have 30 different correct answers. And that's really an observation that's worth writing down. I'll just make a quick remark here. The row echelon form of a matrix is not unique. So there can be many answers. There can be many of them. However, although there can be many of them, however, every correct row echelon form for A, every correct answer for a row echelon form for A will have one thing in common. Okay, so we've got 30 people in here. We could have 30 different correct row echelon forms, but they're all different final answers. But there's one thing about them that we will all agree about. And I'm wondering if anybody, there's no reason why you would necessarily know this if you haven't seen this before, but does anybody have a guess as to what it is about every correct row echelon form that would be the same? All 30 of us would agree about it. Joel?
Explain. We're like
The solution to the system at the end of the day, that is absolutely true, because after all, it is just one linear system. So it would have a unique solution, but even just forget about the linear system for a minute, just on the matrix itself, would there be something about every correct final matrix that would be the same? You have an idea? The first pivot point, we're getting onto the right track here. I want to get a little more specific. Go ahead, Isaac.
Would it be the bottom row being zeros?
That is basically what I'm after. The fact that there is a row of zeros. Everybody would get, all 30 of us would get a single row of zeros. In other words, does anybody want to rephrase that for me in an even sort of more succinct way? Yes.
If the matrix isn't a square, you're always gonna get a row of numbers.
Not necessarily. Not necessarily. Joel? There we go. There we go. The number of pivots is going to be the same, which is the same. Somebody said that the rows of zeros would be compatible. So here we have one row of zeros. All 30 of us would get one row of zeros, no matter which EROs we did. And we would all get 2 pivots. It's the number of pivots. This is so important. The number of pivots. That's the point. That is the point. And that is such an important value in linear algebra that it has a name. The number of pivots is called the rank of the matrix. Okay, so that's a word we want to know. So this is called the rank of A. Everybody's got to agree on what the rank is, no matter which EROs that you did. So in our example above, the rank of A is in fact just 2. See,
So immediately challenging that statement, obviously no education prior to this from that. So I see your reference has 2 rows of 0, right?
it did, yes.
So there is no way that that second to last row will have numbers.
Correct.
And another pivot.
That's right. That's right. We would all have to go through the motions of whatever EROs we chose. We might not do the same EROs. We might not get the same row echelon form, but we will all look at each other's row echelon form and we'll all have 2 rows of zeros. Has to be. The math has to work out that way. This is actually not an obvious remark. If some of you are like, I don't know, I don't see why that should be true. That's fair. That would be fair. I'd be like, you know what, you're right. It is not really obvious. This is something that on a more theoretical, pure math basis, we would have to justify. I'm not going to go down that road right now, but it would be a really good, deeper dive to take. Why is it that we have to agree about how many pivots we have at the end of the day? It's a really good point. Yeah. These are great questions. I love all the feedback, all the comments. Is everybody good so far? Yeah.
Is there a way to get, like, know how many, know the value of your rank?
Before you even
Before
start,
that?
there really isn't. There really isn't. you wouldn't look at this matrix and say, oh yeah, the rank is gonna be 2, right? I know that it won't be more than 3, because you can't have more than 1 pivot per row. So if I only have 3 rows, then at most I could only have 3 pivots, but I can't really say anything deeper than that, right? I just can't glance at it and have a good idea how many pivots it would have. Yeah.
But it has to be more than, one, right? It has to.
That we would be able to say at this point, but like I could give you examples where the rank of the matrix was 1. If I had a matrix of 1, 1, 1, 1, 1, 1 all the way across, and then the next row was 2, 2, 2, 2, 2, 2, 2, 2, 2 all the way across, then that will only end up having 1 pivot at the end of the day.
So if I took an educated guess and tried to say, oh, there's only 1 pivot for that one, what issue would you see me running into as I try to make that second row zeros as well?
To make the second row zeros directly from the first one alone, what would actually have to be true is it would have to be a multiple of the first row. So like 1, 1, 1, 1, 1 versus 2, 2, 2, 2, 2, which is not what we have here. I can kind of just tell that I'm going to get 2 pivots out of the first 2 rows. But what I can't tell is that somewhere along the line, one of my rows is going to get totally zeroed out. That actually isn't really obvious just looking at it in the first place. There is so much more to say about this when we get a little deeper into it. Like, what does the rank really mean? What does getting a row of zeros really mean? What does it tell you about your system of equations? All that kind of stuff. So I'm definitely gonna come back to that. Okay. I need to close the loop. I only have about 6 minutes to close the loop on the big picture of, well, how do we use all the stuff we've just learned to actually solve a system? So let me write an example down and show you how this process that I've just been talking about, how it actually works. And I might have to sort of streamline it just a little bit to totally get to the punchline. But we'll try our best. If I don't get done, it's okay. I can always come back to it on Thursday. But just as an example, and this is actually getting into the next section. This is a quick little example to illustrate the technique that I'm explaining, which is called Gaussian elimination. That is the name of this technique right now. So in
Is that the same?
5 minutes, I'm going to go over what this is. Yeah, so I'm going to just do one quick example and try to get this down, and then we'll come back and talk more about it next time. So let's suppose that I asked you to solve this system right here. 2u minus 3v plus w minus x plus y equals 0. And then the next one might be 4u minus 6v plus 2w minus 3x minus y equals -5. And the third one is -2u plus 3v minus 2w plus 2x minus y equals 3. So this was where the whole chapter 2 started from. If I give you a system of equations, how can you solve for the unknowns? Okay, so let's see if we can do it. The solution, I've already given you kind of the outline of it. The first thing to do is to write down the A sharp. That's literally going to amount to copying the coefficients of the system into an augmented matrix. So I'm just grabbing these numbers and building this matrix right here, as you can see. Okay? -2, 3, -2, 2, -1, and 3. So there is your augmented matrix for your system. Okay. Now the unknowns are not written down anymore in this matrix, but remember, guys, that the unknowns, they are sort of lined up with these columns, right? The coefficients that you're seeing in the matrix are being multiplied by those unknowns, which are the U, the V, the W, the X, and the Y, that are kind of lined up with those columns. So the first thing we have to do is bring this into row echelon form. And so you've got to do a few EROs. And I hate to bring fractions into it right away by dividing by 2 or 1 or 4 or something like that. So I think what I would probably recommend that we do here is that ultimately this 2 will be turned into a 1 by multiplying by 1/2. Just like I did on this example, I finally multiplied this 3 by a 1/2 to turn it into a pivot at the very end. So I might be thinking along the same lines. Eventually I'll multiply the first row by 1/2, but let's leave it as a 2 for now. And let's just do a 1, 2 of -2. Okay, I can tell right now, we're not going to quite finish this today, but I'll just make a couple of points here and then we'll come back on Thursday and finish it. If I take -2 times the first row and I add it to the second row, I will get 0. So the reason I'm doing this, guys, how do I know that this is the thing I want to do? It's literally just looking at these two numbers. I want to take that 2 and use it to turn the 4 into a 0. So I take -2 times 2 and add that to 4. Okay, and then I have to go across the whole row and do the same thing, and I'm actually going to get a bunch of zeros. And then a -1, and then a -3, and then a -5. So I'm taking -2 times the first row and adding it to the second row. And then here's the point I wanted to make. We can actually do more than one ERO at a time. Because I already know I want to make a 0 here as well. Right? Because below this is going to be my pivot eventually. It's not really a pivot yet, but it's going to be my pivot eventually. I want to get a 0 down here, so I can just use the first row and the third row and add from the first row to the third row. So I can just add the first row to the third row, and I'll get 0 and 0 and -1 and 1 and 0 and 3. And I find it helpful sometimes to kind of just put my little diamonds around wherever the pivot positions are going to be, even though technically a pivot must be a 1, right? So technically these are not pivots yet, but they are the positions of the pivots. Okay, so all I have left to do from here, guys, to get it into row echelon form is I have to permute the second and third row. And then I need to multiply each row by the appropriate reciprocal of whatever that leading pivot is. So I think what I'll do is I'm going to come back to this on Thursday. So February 5th, we'll come back and do. Once we get into row echelon form, I have to explain how to do the back substitution part. It's not as simple as z equals 4, therefore y equals 3, therefore x equals 11/2. It's a little more complicated than that, and I don't want to rush this. We got to make sure we know how to do it correctly. One warning though, guys, don't go hog wild on doing many EROs together. I don't mind this, but if you start saying, oh, I think I'll permute the first 2 rows, then I'm going to multiply the second row by 5, then I'm going to do 8, 2, 3 of 7. Did you multiply the second row by 5 before or after you permuted it with the first row? I get so confused by that. Do not do this kind of stuff. A couple of A operations together in one step is fine, but don't go overboard with it, or you'll really regret it later. It's hard to avoid mistakes if you go too fast. So, all right, guys, I'll let you go. Thanks. Sorry for running a little over. Appreciate your time today. Have a great rest of your Tuesday, and I'll be around for office hours if you've got any more homework questions for me. Bye for now.